This lecture assumes that you're familiar with the topics that we'll go over in terms of decision trees, random forests, and neural networks, but in a regression context. So you've seen how these techniques can be used for trying to predict some kind of continuous variable like the demand for natural gas. Now we're going to look at some classification problems. Classification problems are among the most interesting and widely applied techniques in data analysis. And you may want to classify things into a number of categories. For instance, a lot of recommender systems like from Amazon for books or Netflix for movies are recommending how many stars you will give this item. But I'm going to look at the simplest ones, which are two-way classifications, classify people into one of two groups. And there's a lot of applicability of this. You may want to predict, for instance, whether somebody will make a sale or not. You may want to predict whether or not somebody will get an illness or whether a treatment will successfully treat a particular condition. Or you may be interested in whether somebody is going to default on their loan or not default on their loan, or make a claim on their insurance or not make a claim on their insurance. So there's lots of problems where you want to classify people into one of two groups and see if you can find predictive variables that help you predict that outcome. One thing that makes this a little bit difficult is that the language that's used in many of these techniques is a very unfamiliar language. And in fact, you've come across it. You probably have heard about articles, especially things in medical journals where they'll say, if you exercise regularly, then your risk of getting a heart attack is 40% lower. Or they'll say the odds of you contracting this disease or this type of cancer is 20% higher if you eat the following kind of diet. That language is a very unfamiliar language, so I want to talk about the language first of all. And for this, I'm going to start with the one particular data set. This is the data set for the Titanic. And it actually shows all of the passengers that were on the Titanic and quite a bit of information about them. There were 1,313 people as passengers in the Titanic. There were about another 700 that were crew, and they were almost all male, and they almost all died. But I'm going to focus on the passengers, and in terms of what their survival or death looked like compared to their gender. So we can start with fit Y by X. Does the survival respond to their gender? And so if you look at the row percents here, for the women, about 66% survived, 307 out of the 463. For the men, only 142 out of 850 survived. That's about 16.7%. So clearly, women survived at a lot better rate than men did. But if you look at how this is reported in statistical techniques, here's the language I want to use here. So this table will reproduce what you can get yourself out of the Titanic data set. And so the table is here just showing how many people lived and died of the different genders for the 1,313 passengers that were on the boat. And there are two measures that are usually used. One is called the odds ratio and the other is called relative risk. For the odds ratio, it's computed the following way. So there were 463 female passengers, 307 survived, 156 died. Okay, so the odds ratio down here compares the relative odds of death in each group. So what is an odds? The odds is the probability of, in this case, dying or surviving, whichever you want to focus on. I'll look at surviving here. So the probability of surviving over the probability of not surviving. So an odds is the ratio of two probabilities. The probability of something happening divided by the probability of it not happening. So 156 out of 463 is the probability of dying happening. 307 out of 463 is the probability of surviving for women. So the ratio of the probability of them dying to the probability of them surviving is 156 divided by 307, or 0.51. I did that. That's the probability of them, or the odds of them dying. The odds of them surviving is exactly the opposite. It's 307 over 156, which is 1.96. So you could say the odds of female surviving is 1.96 to 1 against dying. For males, the odds were almost 5 to 1 in favor of death, 708 divided by the 142, 4.99. So this is what the odds ratio is. The odds ratio is actually 9.78. You take the odds for the male of dying divided by the odds of the female dying, 4.99 divided by 0.51. And it would be a true statement to say there is almost a 10-fold greater odds of death for males than for females. Now, if you start with that last statement, if you had an article that was published about the Titanic and said there was a 10-fold greater odds of death for males than for females, and ask yourself, how likely is it that somebody could take that 10-fold greater odds and back up to what it actually means in terms of the fraction that died and didn't? I think you'd reach the same conclusion I do, that almost nobody would be able to go back from that final statement to what the actual calculations were. These are fairly unnatural and multi-step derivations to get to what the odds ratio is. Most people are used to thinking about the probability, so you think about the probability of dying, but the odds is the probability of dying over the probability of not dying, and then the odds ratio is that odds for one group divided by the odds for another group. Another measure that's sometimes used is called the relative risk, sometimes called the risk ratio. That compares the probability of death in each group rather than the odds. So for females, the probability of death is 33.7%, calculated as 156 divided by 463. For males, the probability of dying is 83.3%, the 708 divided by the 850. The relative risk of death then is 2.5. You take the risk, the probability for men divided by the probability for women. So the relative risk is 2.5, and it's a true statement to say there is 2.5 times greater probability of death for males than for females. So both of these bolded statements are in fact true. I think you can look at them and speculate that they might have different impacts on people hearing one or the other. And in fact, in the medical literature, you'll find that there are a bunch of articles, and they are not just about semantics, they're actually some substantial articles trying to say under what conditions it is better to use the risk ratio and what conditions it's better to use the odds ratio. But they are both accurate measures. They just convey the information differently. And neither is a particularly easy thing for the mind to intuit. So probabilities themselves are sort of okay for people to understand. The probability of something happening is how often it will happen. But the odds ratio and the relative risk are several steps of derivation that are not really intuitive. So language. The language is particularly unusual. And in fact, if we want to go here, you can actually get those odds ratios in JMP. Once you do that fit y by x, you can go to odds ratio. And the odds ratio is 0.1 here for, this is, let me see if I can match that up to the words we just had. Yeah, 0.1 is about 10. So odds ratio is about 10 to 1. If you're just flipping, instead of looking at the risk of dying for men, or look at the risk of dying for women compared to men, you get about 0.1, and you have a confidence interval for that odds ratio. An odds ratio of 1 is a critical number, because if it's 1, it says that the odds are the same for the two groups, which you can then back up to say the probability of something happening is the same for the two groups. So odds ratios that deviate from 1 are saying one group is more likely than the other group. And these are pretty far away from 1. The 95% confidence interval doesn't get close to 1. It's pretty clear that the men had a higher risk of dying. You can also look at the relative risk here, and that is actually computed for you. You get to choose which one you want to highlight, but you get a relative risk with a confidence interval. Okay, but that's not the way we're going to be approaching these problems, so I just want to use that as an example, concrete example for the language. A little more language. We're going to see in these techniques that there's something called the confusion matrix. And this matrix shows there's two categories, so we'll call one of them a positive result. You do get the disease, you do make the purchase, you do default on your loan, and the negative means you don't have that characteristic. And in truth, you either have the characteristic or not, and then the model is going to predict that you either will have the characteristic or not. Where we predict a positive result and the truth is positive, we call it a true positive. Where we predict a negative result and the truth is negative, we call it a true negative. A false positive is where we're predicting a positive, but it's not really a positive. And a false negative is when we predict there'll be a negative, but it really is a positive. And one of the main measures we're going to use is something called the area under the curve, and it's kind of derived this way. If you graph the false positives on the x-axis and the true positives on the vertical axis, then we can construct a few points of interest here. The origin, the 0, 0 point, you could get that point if you predict everybody will be a negative. So you produce nobody will have this characteristic. What's going to happen? You're going to have 0% true positives and 0% of the false positives because there are no positives at all. You're not predicting any positives, and so you won't get any of the real positives, and you won't get any false positives. So 0, 0 is one easy point. Just predict everybody will be negative. If you can predict everybody will be positive, then you will get all of the true positives. But of the false, you get all the false positives too, because everybody's been predicted as positive. There are no negatives to deal with. So the 1, 1 point is on there. And in fact, this 45-degree line shows any random prediction. For instance, the one that's shown here in the middle, you could randomly predict half of the people will come out positive and half will be negative. And if it's random, you should sort of on average get 50% of the true positives and 50% of them should be false positives. So you would have 0.5, 0.5. So all the points on the 45-degree line are from random predictions, ranging from predicting everybody to predicting nobody to predicting any fraction in between random. The best point you could get is up here on the vertical axis at 1 with the 0 x coordinate. That's perfect prediction because what are you doing? You're getting all of the true positives and no false positives. So every single person you predict a positive for is really a positive and there are no false predictions. And the reason why the area under the curve is useful is the random predictions of this 45-degree line, and if you calculate the area of that, it's 1/2 the base times the height of this triangle, and the height is 1, the base is 1, so you get an area of 1/2. And for the perfect prediction, you have a square here, and the area is the base times the height, 1 times 1, so you get 1. So any particular classification model is going to produce a curve that's shown like this one called the ROC curve, and that stands for Receiver Operating Characteristics Curve. It's a throwback to computer science literature. But the ROC curve actually traces out for different sort of cutoffs of how you make the prediction. So you could predict, let's say, anybody that has more than a 50% chance of a positive, they'll be a positive. You could change that threshold and say anybody with more than a 40% chance will be a positive. Anybody more than a 30% chance will predict will be a positive. As you vary that threshold percent, you can trace out the ROC curve, and the area under that curve will range from 1/2 to 1. If it's equal to 1/2, then it basically is no better than a random prediction. If it's actually less than 1/2, it means you'd be better off randomly predicting. And the closer it is to 1, the closer it is to a perfect prediction. This is going to be a very useful way to evaluate models. Okay, so with that, let's take a look at a different data set. So this one is a data set for 2,321 fatal auto crashes in California, and this was actually part of the court case after the Ford Explorer with the tires. I'm forgetting which company, Firestone, or I may get that wrong, which tire company it was. But you may remember there was several court cases about whether or not the tires were at fault or the Ford Explorer was at fault or neither of the above. And for now, let's just focus on the first and fourth column of this. It shows the make of the car, which is either, look at the distribution of that, either Ford or not, and the cause of the fatal crash. So we've got 22% of these fatal crashes involve Fords, 77% involved other brands of cars. But the tire cause was only in 1.2% of the cases. And all the other 99% of the accidents, it was not a tire that caused it. So the first level analysis would basically say, is there a relationship between the cause and the make? In other words, does the cause depend on whether it was a Ford or not, as to whether it was tire related? So if you look at the row percents here, of the Fords, a little over 4% of the fatal crashes involved tire causes. For the other makes, it was about 0.28%. And the p-value being very low tells you there's a significant difference. So in fact, it's very strong evidence that there is a relationship between the make of the car and whether or not it was tire related. And in particular, Ford seemed to be associated with tire related fatal crashes much more than other brands. You could ask for a odds ratio here. And the odds ratio is 0.06, which usually it's easy to interpret odds ratios that are greater than 1. We could ask JMP to reverse that for us, but basically it's saying the odds of a tire-related fatal crash were 0.06 as high in other brands as they were in Ford. If you flip that over, 1 divided by 0.06 is about 16. It's about 16 times higher odds of it being tire related if it was a Ford than another brand. That's a measure of how big that difference is. And you have a confidence interval for that. Now in court, of course, Ford and the tire company didn't particularly, well, Ford didn't like this result. I mean, they may have wanted the tire company to be responsible, but they certainly didn't want to argue that Fords had this particular problem. So they brought in the fact that there are some other variables. For instance, one factor is the age of the vehicle. And another factor is how many passengers it was carrying. If you look at the distributions of these, you see that the age ranged from 0 to 5 years, most of the cars being in the 1 to 3 year old range. And number of passengers, well, actually, about over half of the cars had no passengers, just the driver. But one had, or maybe more than one, I think it's one, had 11 passengers besides the driver. So number of passengers may also have an impact on this. And the argument that was made in court was that more passengers, heavy loaded car on the tires made it more likely to have a tire problem. So if there are more passengers in Fords than in other vehicles, that might explain it. It's not something to do with Fords, it has to do with how heavily loaded they were. Similarly, age, the argument would be that if the Fords tend to be older, the older the car is, more likely the tires are older, and if the tires are older, they're more susceptible to having a problem. They might in fact be the tread may be worn down enough that they should have been replaced. So let's just focus on one of these. Let's just focus on passengers. And let's ask whether there's a relationship between the cause of a crash and the number of passengers. This is fit y by x, but it's different than the ones we've looked at so far because the y variable is nominal and the X variable continuous, and that's this lower left-hand box, logistic regression. It's a different analysis than we've seen so far. Now, the reason why a different analysis is done here is if you could change cause to a 0 or 1 variable, and you could try to fit a line through this, but cause only has 2 values, and it's either 0 or 1, and fitting a line gives you the unrealistic idea that you could be like 0.5 or 0.4 when you're either going to be 0 or 1 on cause. And it's also going to give you predictions that are less than 0 and greater than 1, and there's only 2 groups. So in fact, what's fit here is called logistic regression, and is the subject of a Nobel Prize that was won by Daniel McFadden, forget the year, but he won for developing the technique of logistic regression. And you can see that in the little picture here, the curve that's drawn, it's an S-shaped curve, backwards in the camera, an S-shaped curve. And the S-shaped curve is supposed to give you an estimate of the probability of somebody being a 1 rather than a 0. Probability of being the positive rather than the negative. And so at low, if there's a relationship, you might expect that if, let's say this was people's income versus whether or not they make a purchase, that at very low incomes, the probability rises, is fairly low, but it starts rising more and more quickly as income goes up. Let's see if I can do this in reverse. And then the probability starts growing, but you reach an inflection point when higher and higher income keep contributing to the probability, but it's leveling off. Until you reach the highest possible income, then anybody that is that income or below is sure to make a purchase because you've got everybody in that group. So let's just see what logistic regression looks like here. The curve looks backwards from what it did in the previous picture, but in order to interpret this, you have to be careful about how the curve is drawn. It's actually showing the probability of it not being a tire related to the number of passengers. More passengers not being a tire starts off up at 1, but then drops. There is a p-value. Immediately you can see the p-value, and the p-value, which is repeated down here, is showing the same thing as it did with normal linear regression. It's testing the hypothesis that there's no relationship, in this case, between passengers and the likely cause, and whether or not the accident is caused by a tire problem. So it's testing the hypothesis that there's no relationship between passengers and that, and a low p-value is telling you that you can reject that hypothesis. This is far enough away from 0 to safely say there is a relationship. And the negative relationship, now you have to be really careful how you interpret this, because right underneath it, it says, for the log odds of not tire over the tire. So not only is the odds ratio hard for your intuition to accept, this is the logarithm of the odds ratio. So rather than try to interpret what .55, negative .55 actually means, because it will not settle in your mind very well, forget about the fact that it's a log of the odds and just think about it as not tire versus tire. And a negative sign means that it is less likely as passengers go up that it will be not tire rather than tire cause. So more passengers, less likely it'll be not tire rather than tire. Direct way of saying that is the more heavily loaded the car is, the more likely it is there will be a tire-related fatal crash. And from this, you can get the odds ratios. And when you ask for the odds ratio, you get 2 different odds ratios. The first column is called the unit odds ratio, and this one for a continuous variable is very difficult to interpret because it's basically saying an increase of 1 passenger, 1 more passenger in the car, changes the odds ratio by 0.57, which I won't try to put the words to it. I usually jump right to the second column, which is missing a word. It's actually the range odds ratio. It's comparing the most likely the smallest number of passengers with the highest number of passengers. And so the smallest number of passengers is 0, where you had just a driver. The largest was 11. The difference in the odds ratio between 0 passengers and 11 is 0.002, meaning if you flip it over again, so it's a number greater than 1, it's 500 times as, the odds ratio is 500 times as large if you had 11 passengers than if you had no passengers. So for a continuous variable that has pretty long, skewed, long right-hand tail, you will find a huge odds ratio compared to range. A 1 unit change, though, is hard to interpret. I mean, 1 more passenger, but it's a nonlinear function, so the interpretation depends a lot on where you are on the curve. So you can use this for predictions, as we'll see in a minute, but rather than, if you don't want to look at predictions, I think the intuition that I'd stop with is it's a significant variable, has a negative sign, and it's a log odds of it not being tire-related versus tire-related, so we know that more passengers contributes to it being tire-related. The quantitative size of the estimate is a lot harder to pin down intuitively and might be better. There's an inverse prediction possibility here where you can actually put in some values and see what the predictions look like, and that would make it a lot more concrete. But let me jump ahead, because what we really want to do is not just look at number of passengers, not just look at what the make of the cars, and not just look at the vehicle age. We want to look at all of them. And just like we did multiple linear regression, if we go to fit model and put a cause in as a y variable that's nominal, and take all 3 of these variables and put them in as effects, the personality, you'll notice, is nominal logistic. It's going to do a logistic regression with those 3 variables trying to explain the cause. And so when we run it, you'll notice that if you come down to parameter estimates, they are all highly significant. So all 3 variables belong in the model. This is if it's a Ford rather than another compared to the average of all cars. So if it's a Ford, the negative sign is telling you the log odds of not tire over tire. So it's saying that if it's a Ford, it is less likely it will not be tire. In other words, it's more likely to be tire related with Ford. Significant. It's more likely to be a tire related accident if the car is older. And it's more likely if it's more heavily loaded, all 3 significant. So even though the age and the passengers are contributing factors, it remains true that even after you adjust to those, the Fords are far more likely. How much more likely? Well, you'd want to look at something like the odds ratio then. And so even taking into account, so you get odds ratios for the passengers, for the vehicle age, and here's for the make. So if you compare Ford with a level 1 other compared to Ford, basically the Fords are anywhere from 7 to 54 times as likely to have a tire-related accident. And the reason why I use the top numbers rather than the bottom ones is, remember, this is all for the log odds of a not tire over tire. So if it's not tire over tire, then we're comparing other to Ford. That's the same thing as comparing Fords to others for tire versus not tire. So 7 to 55 times larger odds for a Ford to be involved in a tire-related fatal accident. Let me show you the ROC curve. And it doesn't really matter which one you pick, but let's just think about it being tire-related. So here's the ROC curve. And remember, 0 to 1, this would be this connecting the ends of this square would basically be random guessing. This point up here, it would be a perfect model. The area under the curve is 0.91, which is actually quite good as far as area under the curve. That's a pretty high one. So We'll be able to compare that to other techniques here in just a couple of minutes. So that's the area under the curve, and let's just also look at the confusion matrix, which doesn't look quite so good. For the actual, not tire-related accidents, this model predicts 2,290 would not be tire-related. It makes a mistake and predicts 4 of them would have been tire-related when they weren't. For the tire-related accidents, only 3 out of the 27 tire-related accidents were correctly predicted by this model. So even though the area under the curve is quite high, if you look at this, we're mainly interested in could we predict the tire-related fatal accidents, we can only predict 3 out of 27, 1/9 of them. 90% of them we miss. Overall, if you talk about accuracy, you could say this model is 99-point-something% accurate because, look, there are 2,293 correct predictions and only 28 wrong ones. Anytime you have a rare event, it's easy to get accuracy in terms of getting most of the predictions right. In fact, the easiest way here, you don't need a computer at all. Just predict none of them will be tire-related. Since only 27 are tire-related, you will get 99% accuracy simply by predicting nothing would be tire-related. So measuring accuracy by how many of the predictions are correct is not a good method, except in rare cases. Sometimes when you're looking for something that happens about half the time, measuring accuracy by what percent are correct predictions might be okay. But when it's lopsided like this, this has very high accuracy measured by percent of predictions that are correct, but of the ones you're interested in, it predicts very poorly. However, the area under the curve is still useful information because it's actually telling you that this model might be able to do a better job than what's shown in this confusion matrix. The confusion matrix is based on a prediction that anything with more than a 50% probability of being tire-related will be predicted to be tire-related. If you want to see those predictions, you can go to Save Probability Formula. And what JMP puts in the table is this is the key column for its calculations, but not one you want to interpret because it has to do with the logarithm of the odds ratio. But it gives you for each of these accidents the probability it would not be tire-related, the probability it would be tire-related, and then it automatically in this column assigns whichever probability is greater, it predicts that will be the outcome. So if the probability is more than 50%, it will produce that it will predict that it was tire-related. Let's just see what the probabilities look like. You have to expand that by clicking on that little arrow. Probability of it being tire-related. The median, half of these accidents, there's far less than 1% chance prediction, the probability that it would be tire-related. In fact, 99.5% of these accidents is less than a 32% chance that it would be tire-related. It's only in that very last 0.5% that you get the probability to be greater than 0.5. It's these ones right out here. Those are the only ones that are being predicted to be tire-related. In fact, if you want, we can look at those. And notice that for the most part, they're pretty old. They're 5-year-old cars. There's a couple that are younger here. They're pretty heavily loaded, 4 passengers in each of these, and these have more passengers. They're newer cars, but 6 and 9 passengers each. As it turns out, only half of them turned out to be tire-related. The other 4 actually were not. But the model is predicting a fairly high, over a half probability that they would be tire-related. So it may be possible in this particular, it may be possible in this particular data set to go back in and by hand say, well, maybe if we want to get more of those tire-related accidents, maybe we should make the cutoff somewhere over around, somewhere down in this range. Maybe predict that all of these would be tire-related, and you might get a better prediction of the tire-related accidents. By definition, if you move the threshold from 0.5 to a lower probability, you will get more of the true positives, but you will also get more false positives. There's no way of avoiding that. But most of these problems that you're going to analyze are not symmetric. In other words, making a mistake with a false positive and a mistake with a false negative are usually not equal in terms of their importance. They're usually quite lopsided. And you'll see that real clearly in the next example. Let me show you one other output you get from this model, and that's a lift curve, very useful in marketing. But the way you think about a lift curve is it splits the data into deciles, 10 percentiles. So the top 10%, the next 10%, the next 10%. Measured in terms of the probability of it being tire-related. So this blue curve for tire-related is basically showing that if you targeted the top 10% of the accidents in terms of the likelihood of them being tire-related, you would get 60%. The lift is six times the 10%. You get about 60%, actually a little more, it looks more like 70% of the tire-related accidents. So just imagine how you could use this. If you had this information before the cars were on the road, you basically could target that top 10% of the probabilities, and they're probably going to be cars that tend to be older, quite a few Fords, and ones where a lot of passengers are in it. And you could, for instance, pull them off the road before they have their accident, prevent the accidents, and you get 70% of the accidents prevented by targeting the top 10% of these vehicles that were involved in accidents. Of course, the problem with that is 10%, we're talking about something that happens very rarely, less than 1% of the time. To take 10% of the cars off the road because they are more likely to have this tire-related fatal crash than, or among the most likely to have that, you're basically taking a bunch of people off the road that want to go somewhere and interfering with their lives. So you may not want to do that, but the lift is one way of measuring how useful this information is for targeting just those with the highest probabilities. How much lift do you get? How much of a multiplied effect? If you randomly targeted people, the lift would be equal to 1. Because if you targeted 10% of the cars randomly, you should get about 10% of the accidents in question. So a lift of 1 means it's random. Greater than 1 means your model's doing better than random, and if you want to target some smaller percentage, how much you can actually classify the true positives out of that. Okay, in order to compare the methods, though, I want to switch to a different data set than the Fords. So I'll go through all this again and the other methods as well in this data set. This is actually a random sample from a much larger data set. It was part of a Kaggle competition actually a few years ago. There were 150,000 people that they gave information on. I've taken 10,000 out here mainly so these models will run a lot faster. Some of these take some time, and they took on my computer about a half a minute each, so each of the analyses would probably take about a half minute, but they'll be very quick with 10,000 rows. What we have is information on the variable of interest here, which is whether or not somebody got in serious financial delinquency within a 2-year period. Think of it as bankrupt. They declare bankruptcy. The other variables all have to do with their credit status. And I have definitions behind these columns. So revolving utilization, this is the total balance they have on credit cards and personal lines of credit except for real estate. divided by the sum of the credit limits. So how much of their credit limits they have used up. And if you actually scroll through that data, you'll find that some people have used way more than their credit limit. I'm not quite sure how that happens, but I guess they're able to go over the limit, some fairly extreme. I haven't cleaned this data up. There is a fair amount of cleaning that really needs to be done to analyze it. The age of the person, this is the number of times the borrower has been 30 to 60 days late, but not longer than that in the last 2 years. This is monthly debt payments, alimony, living costs, all divided by monthly gross income, the monthly income, number of open credit lines, number of times have been more than 90 days late, number of real estate loans, and including home equity loans, number of times it was 60 to 90 days late, and the number of dependents they have. All potentially could impact serious delinquency. And so what I'm going to do is run a series of models here. I'm going to start with different than a logistic regression just because I get some different options here. So we're going to find these options under modeling. And the first place I'll go is to the partition methods. And remember, I'm assuming that you've been exposed to these methods, so this is not totally new as to where these are. So the first method I'll look at here is a boosted tree. And we will put a validation portion. We're going to split this data set and pull 30% out as a validation set that the 70% is used for training the data. We're going to try to explain serious delinquency as a function of all of these. There are some settings here. I will, in class, talk about these, but I would just say at this point, the defaults work pretty well. And there are ways to explore whether you want to change the defaults that I will show you. But the defaults are not a bad starting point, so let's just take them. Here is the analysis. You get a confusion matrix shown right away for the training data set and for the validation. So this is what you're really testing it against. And actually, as a baseline, let me just look at the distribution of our serious delinquency. About 7% of the people went bankrupt. So that's what we're trying to forecast. Can we identify that 7% by characteristics so that we can somehow reduce that? So you see in the validation set that there were 32 people that actually went bankrupt, and we have, no, it's the other way around, it's the row. So actual 209 people actually went bankrupt. We have correctly predicted 22 of them with this model, which doesn't sound very good. The ROC curve, the area under the curve, actually comes out to around 0.86 in both of these sets. So that's not bad. That seems much higher. So one thing that might occur to you is maybe we could do better. I mean, with the AUC that high, why are we predicting so badly? So there's a very nice feature here. This is why I did the boosted tree first. Specify profit matrix. These are not symmetric errors that we make. So let's make up some numbers and put them in here. Suppose we predict that somebody will not get in financial delinquency and they actually don't. How much money do we make from them? Let's just say we make $100 profit off of this loan. And over here, in this cell, another correct prediction, we predict that they will be bankrupt, and they actually do go bankrupt. Presumably, since we're using this model beforehand, we predict they'll go bankrupt, we don't give them the loan, they don't go bankrupt. Basically, we make no money off them, we haven't given them a loan. Now, what happens if we predict that they will go bankrupt, but they actually don't? Since we predicted they'll go bankrupt, we don't make them the loan, and I would say, well, we're losing $100 profit that we could have made. And here's the big one. We don't predict that they'll go bankrupt, but they do. We make them a loan, they go bankrupt, we lose a bunch of money. Let's just say we lose let's make it $700. So there's a profit matrix. You click Save the column as property, click OK. And now if we go to Save Columns and Save Prediction Formula, what you get are a lot of columns here. Let me look on the left side so you can see what they are. We first get a prediction from the boosted tree of the probability that they will get in serious financial delinquency, they will go bankrupt in the next 2 years. We get the probability that they won't. We get a most likely prediction, which is simply based off which probability is higher. You know, is the probability that they're going bankrupt greater than 50%. Then we get the profit if we predict that person would be a 0 and if they would be a 1, and we get the most profitable prediction for each person. We get the expected profit, which is based on a prediction, and the actual profit. The actual profit is the final measure here. If we use this model and use that profit matrix, it's the actual profit that we will get. So what you might want to compare here is, for instance, the most profitable decision or classification with what's most likely. So most likely, remember, is based on a 50% cutoff. Basically what the profit matrix does for you is it changes that cutoff. And since we have an asymmetric return here, we're making a false negative is far more costly than a false positive. False positive, we just don't make a loan and don't make the profit. The false negative means we make the loan and they go bankrupt, so we lose a lot of money. So that asymmetry means that we will shift the threshold. The computer's shifting the threshold for us. And so what you can see is that of those that we predicted would be most likely to default, the most profitable prediction is to predict that they will all default, because we're going to lower the threshold from 50% to something lower than that. So we're going to go along with that prediction for all of them. But of the ones where it was less than a 50% chance that they default, we have now shifted 531 of those 9,362 people into a prediction that they will default. We're willing to make more mistakes and with false positives in order to have avoid some false negatives. So we have changed our predictions here. What you'd want to know now is how does it compare to the actuals? So let's just do fit y by x. Let's compare the most likely, the most profitable with the actual serious delinquency. So the actual serious delinquency is the second row of these tables. And you want to know what % of them were predicted correctly. So we only got 10% of the true bankruptcies predicted if we go with the most likely prediction. If we go with the most profitable prediction, we actually are predicting 42% of it. So we've done a lot better. Of course, it came at a cost. It came at the cost that we also have more false positives, so there are people we're not making loans to, but those are fairly cheap mistakes compared to the other mistakes. So we're able to avoid a lot more of the more serious mistakes here. So that profit matrix is actually quite useful, and we'll continue to use that in these other techniques, which you'll see now. So I don't need that one. Let's pull this one up again. So let's compare another method. Oh, I thought the dialog got saved. Okay. Let's go to modeling. Actually, let's go to the logistic regression that we've just looked at. We're going to try to predict serious delinquency using same set of variables. Get a logistic regression. We're going to save probability formula. And I may want to get a lot of columns here, so I may want to label these. This is the first actual profit column was, oops. Guess I have to do it up here. Actual profit, boosted tree. Actual profit from the logistic. So that's two methods. We have two more we're going to look at. Let's look at a random forest, called the bootstrap forest. We'll keep a 0.3 validation portion. Same variables we're going to use, the original variables. Keep all of the defaults for this. Notice the confusion matrix on this, kind of interesting. This particular, the random forest is predicting almost nobody will default. It's putting everybody predicting in the zeros. Only 2 people does it predict in the 70% training set, and only 2 people in the 30% validation set. Despite that, the area under the curve is about 0.89, so this model, I'm going to guess, is going to do a lot better if we allow it to worry about the profit matrix and the asymmetry of errors here. So if I go to save columns, save prediction formula, I believe we will now have another actual profit column, which we will call profit random forest. And one more technique, again, remember I'm assuming that you have basic familiarity with what these techniques are. We'll use a neural network, same set of variables. We will keep the defaults that are shown here. For some reason, this platform allows you, instead of looking at the numbers in the confusion matrix, you could also look at the rates. So in fact, this is of the series defaults, the model and the training data is correctly predicted 11% of them. I think if you remember, the logistic regression got about 10% of them, I think. The 15% in the validation set, so they actually did a little better there. But that's based on the sort of 50% cutoff. If we look at the ROC curve, well, it's lower than it was on the last one, 0.81, 0.83. Some of those settings might improve that. You want to look at a lift curve for a minute, just as an example. If you targeted the 10% of the people that were most likely to default according to the model, you would get about 45%. You'd get almost half of the actual defaulters. Of course, 10% of the people is a lot of people, so if you deny loans to 10% of them, you're giving up quite a bit of business. But we'll let the model handle the profit matrix by going to save formulas. And make sure I got the last one, yeah. So this is profit neural net. Let's just see how the profits compare. The easiest way to get that would be a table summary. And what I'm going to do is pick the profit columns that I just, actual profit, boosted tree. We'll look at the sum, total profit, so that's across the 10,000 people. Actual profit from the logistic. Profit from the random forest. Profit from the neural network. And if you don't put a grouping variable in, you'll just get those totals. And rather than look across, why don't we transpose that? And even with 4 numbers, probably easier to look at a picture. So there is some difference here. The random forest seems to have produced the highest profit here, followed by the boosted tree. Logistic is the worst. That's a pretty consistent pattern. I find logistic does not nearly do as well on classification problems as these other techniques. And the neural net usually does better, but in this particular case, it might be that some of the default settings could significantly improve it. But one important point is there's no general results in this. You will not find that everyone says use a random forest or use a boosted tree. It depends on each separate data set. So you've got the tools to look at them all. I would suggest doing that because there can be very big differences between these techniques, and it may be dependent on what particular data set you're looking at. Another comparison you might want to look at here, and let's do it through the multivariate platform. Let's just see how the probabilities compare for the different methods. I won't worry about labeling them right now, but let's just look at probabilities of getting ones, in other words, bankruptcy for each of the 4 techniques. And the only thing to point out here is that, in fact, there's I didn't even label them very well, so I don't know which came from which models right now. You can see that this one and this one are pretty close, certainly not exact. There's a lot more variety with the others. So different people are getting allocated or predicted to be in bankruptcy differently by the different models. So there really is a difference between the models in terms of how they predict. If you believe in the idea of the ensemble methods, you could take it a step further and say, well, I've got 4 different methods here. Why don't I average the 4 probabilities and use that? And that would be a legitimate approach to then do an ensemble of the 4 different methods, since they do treat individual people somewhat differently. Okay, let me show you one more thing, and then I will leave it for now. There's a lot of material in here, and there's a lot more work to be done, but let's look at the bootstrap forest one that I ran. One feature JMP has is that any analysis you do, there'll be an option at the top red arrow for a script. And the scripting language behind JMP is actually quite complicated, quite rich, and takes a long time to study. But one of the quickest ways to get into it is you can go save script to script window, and it will save a script of what you just asked for. So what did we do here? These are the commands that we just put in, and it's saved as a script. You could save it and then open it later on, and there's a run script button. But the other thing you can do that actually is quite handy here is if you wanted to investigate, let's say, look at minimum size split for the tree where it says 10. Let's say you want to know how does it change the results if I went from like 5 to 15? Is that an important component of this model? Does it change the results significantly? So what you could do is you can put, and you're probably all familiar with the idea of sort of do loops back from some computer programming days, but you can do a loop in this script window pretty easily. You do for I equals 0 and I less than, let's say 4. I just don't want to run it too many times. You could easily put a lot more ones in this. The I++ is telling Jump to iterate this each time to start with I equals 0, then go to I equals 1, I equals 2, I equals 3, and then stop. Don't want to close the parenthesis yet. You do want another closed parenthesis at the end, since we've opened a parenthesis at the top. And now where do we want to put I? Well, let's say it's the split size, so instead of saying 10, let's go 5 plus 2 times I. So with I at 0, 1, 2, 3, we'll be looking at split sizes of 5, 7, 9, and 11. Should give us an idea whether the split size matters much. So that's the only thing we have to change. We put the 4 at top to tell it to do a loop. Close parentheses at the back to match the one at the front, and here's where we put I to change the minimum split size. You can click the button for run script, and it's going to run this 4 different times. And now perhaps the easiest way to see this is if you check these boxes on each window, which is saving them for arranging them. And then let's go I haven't tried that one. I don't like that one. I don't know what happened. Okay, let me do the arrange selected windows. It's going to spread across 2 of my screens here, so you won't see 2 of them, but I can see all 4. And so, for instance, let's say you wanted to compare the area under the curve. For the validation set, I get 0.86. Well, it starts on my right here with the splits for tree. Let's see. Oh, minimum split size 7, 9, 11 here, and oh, here's the 5. So the first one, less splits per tree, got 0.86. I go to the 7 splits per tree, which you can't see, but I can. I get 0.87, the area under the curve. For 9 splits per tree, I'm getting 0.83. It goes down a little bit. And 0.85 with the 11 splits. I don't see a lot of change. So this particular experiment leads me to believe minimum splits per tree is not going to be a key setting. So you really have to explore the other settings to see whether some of them might produce much better results. From my experience, which is somewhat limited on this, I would say that I find the defaults work pretty well. I have explored things like changing the validation portion. It's at 30%, kind of go from 20 to 40%, doesn't change the results very much. In fact, surprisingly, it doesn't change the results a lot if you don't even have a validation portion. As much as people worry about overfitting, I think the settings are sort of built-in ways to protect against overfitting the model. So in any case, I just show you that that scripting is there. It certainly takes you more time to kind of study scripting and understand how to use that, but it's very nice that whatever analysis you can do, you can automatically have it saved as a script, and then you can learn the scripting language a lot easier by looking at it, and it's pretty easy to put in a do loop so that if you want to do this analysis a bunch of times, it can be done very quickly. Well, I think that's plenty of material for this. There's actually a lot there, so I think we will stop this lecture now. I will definitely be covering some of this in person as well.